Morning, everybody.
Morning.
Class recording has started. Yeah. Want to make sure we're official with it. So. All right. So yesterday we started in on chapter 6, and chapter 6 pulls together two ideas, one being circular motion, the other being universal gravitation. And we sort of mash those together because of the whole satellite motion thing and everything like that. Right? So at the beginning, when we talked about circular motion, regardless of what is causing it, if something is moving in a circle, there are two requirements. First, we have to have acceleration and velocity perpendicular to one another, right? Those are one requirement for something to move in a circle. Because if that acceleration is perpendicular to the way that it's currently going, the object won't speed up and it won't slow down, it is only going to change direction. So if we're going to have something moving in a circular motion that isn't speeding up or slowing down, a perfect circle, it's got to have acceleration perpendicular to velocity. And if there's acceleration perpendicular to velocity, there has to be force perpendicular to velocity as well, right? Because force causes acceleration. Regardless of where that force comes from, whether it's a tension force or whether it's friction or whether it's a string, right? We got to have some force perpendicular to that velocity. And so yesterday we did this problem where we have two forces, the weight force, the tension force, neither one of them perpendicular to the velocity currently, but we have this component of the tension force that is perpendicular to velocity, and that component ends up being the centripetal force. Centripetal force magnitude is equal to mv squared over r, right? So we use some trig, find the horizontal component, plug that into this equation, and then we can solve for the velocity. Good there? All right, so let's move on to universal gravitation. All right, so before we do this, let's go ahead and say anything appropriate or just inappropriate things, as he's now known for. So.
Did you hear about his timeout yesterday?
I did. So heard about the timeout. So. All right. So with universal gravitation, okay, Newton proposes that the force of gravity is a mutually attractive force between any two masses that exist in the universe. Right? The amount of that force, F of g, depends on three things. It depends on the mass of the two objects. Those are both direct relationships. It also depends on the distance between them. That is an inverse square relationship, right? So we talked about the idea that if you double the distance between them, you're actually reducing the amount of gravity to 1/4 of its original value because of the whole squared on the bottom of the fraction thing and stuff like that, right? Newton proposes those ideas that he knows that the force of gravity is proportional to those factors, but not equal, because he didn't know about this, the universal gravitational constant, right? Universal gravitational constant was verified experimentally many years after Newton passed away, but we now know that this value makes the relationship not between force and these factors not proportional but equal. Does that make sense? Right. So then here the value for the universal gravitational constant is 6.67 times 10 to the minus 11th power. That value will obviously be in your formula book. Okay. It's got kind of a weird unit, right? So it's got newtons times meters squared over kilograms squared. That's the unit for the universal gravitational constant. The only reason it has that unit is because when it's substituted in to this expression, all of the units except newtons have to cancel out, because we're going to end up with the force, right? So we end up with meters squared on the top to cancel this meter squared, kilograms squared on the bottom to cancel these kilograms squared. Okay. Good there? All right. So that's the gist of universal gravitation. What we find out is that gravity, being a force that can affect things without contact, is a field force, and so it's subject to field ideas. Okay. We didn't spend a whole lot of time on this, but when we talk about the strength of the field, we always talk about basically force per mass. All right. If in any field, the concept is the same, but what it's per is differing. So like we'll get to a problem today in chapter 5. A gravitational field is force per mass because mass determines the amount of gravity. Okay? An electric field is force per charge because charge is the quantity that's responsible for that field. Is that? Yeah. But we're still taking how much force does this object feel per mass? Okay? And when we do that, we end up with something like this. We have been making this assumption for the force of gravity here on Earth, like for the beginning part of this, for the beginning part of the course. We make this assumption as the force of gravity acting on an object. But in reality, to figure out the force of gravity between any old object and the Earth, we would substitute in the mass of that object, the mass of the Earth, and then the radius of the Earth, because when we talk about gravitation, we say it originates from the center. Does that sound familiar? Okay, so here, if we're going to make this assumption for the force of gravity, it has to equal what value would actually be when we plug it into Newton's law of universal gravitation. All right? This is always the mass of the object, whether it's, this baseball or whatever, right? This is the mass of that object as well. So those two cancel, right? In essence, what we are doing we end up with that, okay? Does that make sense mathematically how I got it? Yep. If we plug all of these values into this side of the equation, the universal gravitational constant that we just talked about, the mass of the Earth, the radius of the Earth squared, you know what we get? 9.81, right? In essence, what we are doing is taking the mass of each individual object out of the picture and just relying on what the Earth is doing to the area surrounding it. This is the strength of the gravitational field, right? And we get it by taking the actual force of gravity and dividing it by the mass of whatever object we're talking about. Force per mass. Does that make sense how we got it, how we get there? Right, and then these cancel, and then we end up with exactly the same thing that we have here. Good? Okay. So, this question is about gravitational fields. Define gravitational field strength. I just did it for you. Right? When we talk about the strength of the gravitational field, what do we talk about? That's not the strength of the gravitational field. That's the strength of the gravitational force. Force per mass. All right. So the gravitational field, if it's Yusuf, if it said gravitational force strength or the force of gravity, that's Newton's equation. But when we do the field, we do this, right, where we have force per mass, and that's anytime it asks you to define field strength, it's always going to be force per mass or force per charge, depending on what object we're talking about. Okay? So it says the gravitational field strength at the surface of Jupiter is 25 newtons per kilogram. Okay? And the radius of Jupiter is 7.1 times 10 to the 7th meters. Derive an expression for the gravitational field strength at the surface of a planet in terms of its mass, its radius, and the gravitational constant, okay? If we just did that, right? Yeah, here, right, in this expression, instead of E's, J's, right, for Jupiter. We're taking this assumption, right, force per mass, right? Here's the force, here's the mass of an individual object, that cancels out, and we end up with this expression. Yeah, that's exactly what we just did. And then, right, so this here, right, here we, like I said, we have E's here, but we, substitute in J's for that if we're talking about Jupiter, right? And then the next question says, use your expression to estimate the mass of Jupiter, right? It told you that the gravitational field strength is 25 newtons per kilogram, force per mass. It told you that the radius of Jupiter is 7.1. That means the only thing left in here that we don't know is the mass of Jupiter, because this is the gravitational constant, which we know, right?
Have you seen The Social Network?
No, I have not. It's one of those movies that you're like, oh, I should see that, and I just haven't, and now it's like 10 years later,
Yeah.
So.
Whoa. Much bigger.
Did we square the radius? It's much bigger than what?
2.6 times 7 something like that. I don't think I squared the radius.
Yeah, make sure you square the radius. That's always a big thing. So. Yeah, whenever we do these problems with gravity, squaring the radius is always the one that's where the problem might come in. So. Okay. All right. Questions there? We'll come back to this answer for comparison in just a second. So. Derive an expression for the gravitational field strength as a function of distance away from a point mass m. That's exactly the same thing, right? Except now, instead of an object and the radius of that object, it's just big M and how far away are we from that object. It's exactly the same expression, all right? The radius of Earth is 6,400 kilometers, and the gravitational field strength at its surface is 9.8 newtons per kilogram. Calculate a value for the mass of the Earth. Yes. Let's do it, though, just for comparison's sake. So now you have two things to worry about in this problem, right? One, make sure you square the radius, but two, they gave you the radius in kilometers, right? You can't have the radius in kilometers, it's gotta be in meters. So, two things before we move on to the next part. No, let's go. We can finish the next part. That's fine. So, all right. It says on the diagram below, draw lines to represent the gravitational field outside of Earth. It says say there's two ways that you can do this, all right? It's worth 2 points, so you're gonna have to do 2 things, all right? The way that they did this in the book is the following. Okay? No, sorry, my bad. No, my bad. Okay. Well, there's 2 ways I think you can do this, okay? Here, you can make a note that closer to the Earth, those lines are closer together, indicating a stronger field. And that farther away from the Earth, the lines are farther apart, indicating a weaker field. Or, I think, you could add another set of lines, another set of arrows, but make those arrows shorter than these arrows, indicating that the field is weaker farther away from the Earth than it is closer to the Earth. Right? But because it's 2 points, I'm thinking you're going to have to indicate somehow where is the field stronger and where is the field weaker. Right? Adding description to the diagram is going to help. Okay, so keep that in mind. I drew my arrows pointing the wrong way on my answer key. So. All right, good there. And then finally, for part D, a satellite that orbits the Earth is in the gravitational field of Earth. Discuss why an astronaut inside the satellite feels weightless. All right, do we... G-force is something different. They're traveling the same speed as what? The satellite, okay? What does that get rid of? How come you're not falling through the floor under the influence of gravity? Normal force, right? If you're being acted on by gravity and a spaceship is being acted on by gravity, you're both feeling that exact same force of gravity. You're feeling the same acceleration, meaning that there is no normal force anymore. Does that make sense? Yes, no, maybe? Right. That's really where the weightless feeling comes from, is not so much from the gravity, but from the normal force. No, not that he doesn't have anything pulling him down, he has nothing pushing up. So, like, if we talk about an amusement park ride, okay, like, let's go just straight up, like the Demon Drop at Cedar Point, right? When you're up at the top, the normal force is preventing you from falling. And then there's a frictional force on the stand of the Demon Drop that keeps the seat from falling. Does that make sense? So you and the seat are not going anywhere. But once we let the frictional brake on the seat go, now both of you are subject to the force of gravity and the acceleration caused by gravity. We know that that acceleration is the same for all objects, right? So now you and the seat are descending at the same rate, meaning that their seat can't push on you because it's falling the same rate as you. Does that make sense? Okay. So it's really not the lack of gravity that makes you feel weightless. It's the lack of normal force.
So that's 3 points.
Say again?
It's got 3 marks.
So I would say probably in this, all right? For 3 points, here would be my guess. One, I would say that there's still gravity. 2, astronaut and satellite experience the same gravitational acceleration. And this results in no normal force. fact that you understand that there is still gravity acting on something, right? But when that gravity and that gravitational acceleration is the same for all objects, that prevents it from applying a normal force to you, and that gives you that weightless feeling, right? You're falling, the satellite is falling, you're just not getting any closer to the floor because they're both falling at the same rate. Good? All right. One thing before we move on, just to make sure. So here's the mass of the Earth, right? And in the previous problem, we calculated the mass of Jupiter, right? Look at it's a huge difference, right? 10 to the 27th power versus 10 to the 24th power. There we go. Right? Yeah, Jupiter is like way, way, way bigger than Earth, right? But the Sun is 10 to the 31st power, so it's like way, way, way bigger than Jupiter. So yeah, just when we talk about masses within the solar system, and yeah, obviously the sun's gravity sort of dominates because its mass is so large, right? The other thing, here, right, 9.8 newtons per kilogram, right? Obviously the number is familiar, but the unit is different than what we've used, right? Here, newtons per kilogram does fit the bill of force per mass, right? That's gravitational field strength, okay? But remember that newtons is a derived unit, yes? All right, do we remember the combination that makes up newton? All right?
Wait, this is acceleration, so.
No. This is newtons, okay? The unit for gravitational field strength is newtons per kilogram because we talked about its force per mass, right? But when you take and substitute in the equivalent expression or the equivalent base units for newtons, which is this, right? Right, because then what happens to your kilograms there? They divide them out, they cancel out, right? And you're only left with, that's what gravitational field strength is telling you basically. What is the acceleration caused by gravity at that location? Because we're depending on the gravity from the object, right? This expression for gravitational field strength only depends on the mass of the Earth and the radius of the Earth. It has no bearing on the object itself, right? The object itself doesn't influence it at all. Good? Okay there? All right. So that's good for for unit 6. So I'm going to stop this recording.